Welcome back. Factoring and Applications Lesson 7, Solving Radical Equations Using Factoring. So this lesson, as presented in the book, has three kind of sections. One, looking at and revisiting restrictions on the variable within a radical equation or within a radical symbol, such as this. And we did look at that in our radical section. We didn't really look at it too deep, but we're going to formalize that in this lesson. The second part is solving these radical equations using graphing. This part, though, I'm going to show you how we do it, but you're not going to have to worry about repeating this later. You don't have easy access to the technology these days, so it's just going to be just more information. But we are going to take these radical expressions or equations, and solve them algebraically. So this lesson has three parts. We're going to focus on two of them and formalize the radical restrictions and learn how to solve these expressions or equations graphically. So looking at these radical expressions, so we can see that this radical symbol is inside that root sign. If you remember when we talked about this in our radical unit, in unit 2, there are certain values of x that cannot work with this. And hopefully you kind of remember that anything that's negative value of x would be undefined, right? So if not theta, sorry, would be undefined, which is just a circle with a line through it. So if any value in here is negative, this is not going to work. So we can look at the graph of this equation, and you can kind of see from the graph what values aren't going to work. So in order to do that, I'm going to use an app called Desmos. If you don't have this app already downloaded, you should probably do so. It's a fantastic little app. It'll be really useful for checking some work when we get into our quadratics unit. But for now, so now I just put this equation in and I go y equals square root of x, and you see we get this line. And this line goes on forever to the right, but then kind of just stops right here. It stops right here where x is equal to 0, and there's nothing to the left of that. So you can see from the graph that x cannot be less than 0. Okay, so from the graph, we can see that not restriction, but the values of which x can be, if I sketch this graph real quick, can't be less than 0. They can't be over here. So question 1, sketch on the grid, sketch the graph, just did. State the domain. Now, again, you're not going to have to worry too much about stating the full domain, but it looks like this. A fancy bracket. We're talking about the x values because we're talking about domain. And we put this little line here. So this tells us we're talking about the domain. And then we say, well, x cannot be anything less than 0. So on our graph, x cannot be less than 0. So we say x is greater than or equal to 0, where x belongs to the set of all real numbers. And then we end that. This is the important part, that you're able to see what the actual domain is. This is just descriptive. This is just description. We're talking about x, and then we say that x belongs to the set of all real numbers, which most of the time we are talking about. Question 3, or the third part, for what values of x is the expression, is the radical expression defined? For what values of x is the radical expression defined? Well, x has to be greater than or equal to 0. This is our restriction, okay? So hopefully you remember a little bit about that from our radical unit. So question B says, consider the radical expression x minus 2. On the grid, sketch the graph. So if we go back to Desmos, and we quickly change our equation to x minus 2, get there we go, y equals square root x minus 2. See what happens to our graph? It shifts to the right a little bit. Now, in this case, our graph stops right here. We cannot have any values to the left of it. So x cannot be less than 2. It can be greater than 2, but not less than 2. So that changes our domain a little bit. It also changes our restriction. So if I just quickly sketch this graph. Oops. There's our graph. State the domain. So technically the domain would look like this. We're talking about x. X has to be greater than or equal to 2, where x belongs to the set of all real numbers. From our domain, we can very quickly just pull out what our restrictions are. X has to be greater than or equal to 2. Okay. Now, this last part, number 4, explain how to determine the restrictions algebraically. So this is the part that I hope you remember from our radical unit. To determine these restrictions, all we do is we take the radicand, just the radicand, and we say that that radicand, so in this case, x minus 2, that thing has to be greater than or equal to 0. Because as soon as this radicand becomes negative, this doesn't exist, right? So we say that x minus 2 is greater than or equal to 0, and we simply solve for x. Remember, we use opposite functions to solve or isolate the variable x. So I'm going to add 2 to this. Because I do it to one side of the inequality, I add 2 to the other side. This is going to give me, these will cancel out. X is greater than equal to 2. So we can get our restriction algebraically. We don't need a graph. There is one thing you have to remember, though, when you're determining restrictions on radicals like this. And that's going to come up in this third example here. And you'll kind of see why there's an important thing that happens. So if we're now looking at question C here, consider the radical expression 3 minus 2x on the grid, sketch it. So we're going to go to Desmos again. So we're going to put in our equation. I'm just trying to figure out my sound here. There we go. Put in our equation. What was it? Y equals square root of 3 minus 2x. Square root of 3 minus 2x. Look at that. See, there's our graph. This time it flips the other way. It's going to the left, but at some point it stops right there at 1.5. In this case, x cannot be bigger than 1.5. So x has to be less than or equal to 1.5. So from the graph, we can already determine what that restriction is, less than equal to 1.5. Remember that? So we know that our graph looks like this. Something like that. Okay. We know the restriction. X is less than equal to 1.5. But let's determine that algebraically. Again, remember, when you're determining restrictions algebraically, we're only concerned with the radicand. So we take our radicand, we say 3 minus 2x. That thing has to be greater than or equal to 0. And we solve for the x. So to solve for the x, I need to get rid of this 3. So I'm going to subtract 3, subtract 3. I'm going to get negative 2x is greater than or equal to negative 3. That's negative 2x, negative 2 times x, right? So to get rid of it, I need to divide. So I'm going to divide by negative 2, divide by negative 2. And then this is the part where you have to remember. These will cancel. That leaves me x. Negative 3 divided by negative 2 is technically 1.5, positive 1.5. You could leave that as a fraction if you wanted. It's 3 over 2. Either or, it doesn't matter. But this inequality sign flips. When you multiply or divide an inequality, that's supposed to be an arrow, an inequality by a negative value, the inequality has to flip. So this is where we get our x is less than equal to 1.5. Okay, so that's the guts of that. So let's, I think there's there's a couple of examples. We're going to look at determining the restrictions on the radicals. So this is the next page, top of page 142. We're not going to worry about doing this graphically, right? We're just going to deal with it algebraically. Algebraically determine any restrictions on the values for the variable in these radical equations. So this only applies if there's a variable within the radicand. And then remember, we're only concerned with the radicand. So we're going to pull out this radicand and we're going to say, hey, you know what? 4x plus 1 has to be greater than or equal to 0 for this equation to exist. I'm going to solve for x, do my opposite functions in reverse order, -1, -1. This gives me 4x, has to be greater than or equal to -1. And then I'm going to divide by 4. This leaves me x is greater than or equal to -1/4. There's your restriction, or the values that make this expression defined. Or there's all kinds of terminology depending on what unit you're in. Non-permissible values is another thing, right? So those will come up in a different unit, but this is the restriction for this radical equation. Let's look at B. Square root of 2 minus 5x minus 7 equals 0. Again, we are only concerned with the radicand when we're looking for restrictions, just this. This does not matter to us. Okay. So we take our radicand, 2 minus 5x, greater than or equal to 0, and we solve for x. We're going to subtract 2, subtract 2. Those 2's will cancel on the left-hand side, giving me -5x, greater than or equal to 0 minus 2, -2. But then here, remember, when you divide by this -5, both sides, the inequality has to flip. So these cancel, gives me x. -2 over -5 is just +2 over 5. But this symbol has to flip the other way because we divided by a negative value. There is your restriction. X has to be less than or equal to 2 over 5. And at this point, I would leave these as decimals. I wouldn't worry about, fractions. I wouldn't worry about converting them to decimals. It's not much point in doing that. Okay, so question C, 12 minus square root 24 minus 5x equals 3. Again, we are only concerned with the radicand. This and this means nothing to us when we're looking for restrictions. I take that 24 minus 5x. That has to be greater than or equal to 0. I'm going to solve for the 5x. I'm going to subtract 24. Those will cancel. Minus 5x greater than or equal to -24. And again, because I'm dividing, or let's state in red, sorry. I'm dividing by -5, divide by -5. Those will cancel. X, -24 over -5 is going to be +24 over 5. But my inequality symbol flips, less than equal to. So that's the important part that you have to remember. When you multiply or divide by a negative, you have to flip that inequality. So just very quickly, I'll show you how we can do these or find the solution graphically. But again, you're not going to have to worry about doing this. You're going to have to know how to do it algebraically. So if we take our radical equation, and if we create in our graphing calculator, or whatever it happens to be that we're working with, two equations. One equals y equals x squared root of x plus 1. And the other one, oh, there's my pen, mine's going all funky. Y equals 4, we'll see what happens. X plus 1, right? Square root of X. Come on, Desmos. There we go. Y equals square root X plus 1, and Y equals 4. So now we have two equations on our grid. And if you remember from the solving systems unit in grade 10, when we're solving linear systems, we're looking for the point where those two lines crisscross. It's the same with solving any other set of equations. We're looking for the point where these two lines crisscross. So if I just slide my grid, tap that intersection point, 15. So our solution to this system is 15. So we already know that. We can find that very quickly graphing it, provided you can graph quickly, right? But like I said, you're not going to have to do this. You don't have the technology, but it's a quick, good double check for you if you're doing this work on your own and you have this app downloaded somewhere. So we know we're looking for the number 15. That's how we would do that graphically. But if we flip the page, I think it's the next page, investigation 1. Let's solve that same equation, square root of X plus 1 equals 4, algebraically. So we're looking for the number 15. We know our solution is 15. How do we get there? So first of all, whenever you're doing things like this, it's a good idea to do your restrictions straight away. X plus 1, X plus 1 has to be greater than equal to 0. We're going to minus 1, X has to be greater than equal to negative 1. So this is going to give us some parameters to the solution we find to make sure that our solutions fit. Okay? If our solutions don't fit, we get something called extraneous roots, which is coming up on the next page, I believe. Okay? So in order to solve these radical expressions or equations, we need the radical by itself on one side of the equal sign. Everything else has to be on the other side. So in this case, it's already laid out for us, but we're going to do one. I hope we're going to do one. I think we are. We're going to do one where we have to move some stuff. Yeah, next example. Okay. So because this is already isolated or set up for us, our next step, in order to get rid of this radical sign, this radical symbol here, I need to square this side. Because I square this side, I square the other side. So this is what this step is. So we're going to square both sides. When we square both sides, remember, squaring a root sign, well, that's what it is. From squaring a root sign, the root sign disappears. I get X plus 1. And then 4 squared is 16. And I solve for X. I'm going to subtract 1. Those ones will cancel on the left-hand side. That leaves me X. 16 minus 1, 15. Look at that. There's our solution. That's how we can get there algebraically. But one other step that we have to add in, because we are manipulating this equation by squaring sides, we also need to make sure that we verify our solution. We have to make sure that the solution we found fits with the actual equation that we start with. Like I said before, and it's coming up, sometimes we end up getting solutions that actually don't work. Okay? So, but once we verify them, we can see that they don't work. So technically it's not a solution. So in order to verify, there's two things that you should do. One, quick check. If we say our solution is X is equal to 15, does it fit our restriction? Is X greater than or equal to negative 1? Yes, it is. So there's one check. Okay, we're good to go. But then we need to specifically test or check or verify this number 15. So I go to my original equation, which was square root of X plus 1 equals 4. And I put in 15 for X. Square root of 15 plus 1 equals 4. And then I solve the left-hand side and the right-hand side independently. When we're verifying, I don't move stuff left to right. Okay? I just want to see if the left-hand side equals, I want to see if the left-hand side equals the right side. Okay, that's our process of verifying. So 15 plus 1 is 16. So this is square root of 16 is equal to 4. Square root of 16 is 4. So this solution of 15 is verified. It is a proper solution to this equation. Let's look at question number 2, or investigation number 2. And here we have 3 plus square root x minus 1 equals x. So it says to determine the roots of the radical equation, so the roots are the solutions, and verify the solution. So first of all, because we have this 3 with the radical sign, our first thing is to isolate the radical term. So we need the radical thing by itself. So I'm going to subtract 3 from this side, subtract 3 from this side. So that's how they got to this point. From here, in order to get rid of this radical symbol, I need to square both sides. Square both sides. Okay. This is x minus 3. I have to square the whole thing together. Okay. We get to this situation right here. Square root of x minus 1 all squared is equal to x minus 3 all squared. Now again, remember, squaring a root sign, squaring a radical disappears, makes it disappear. X equals, minus equals this squared. Hopefully you remember, because you hear me saying, what does that mean? X minus 3 times x minus 3. So from here, we expand the right-hand side using FOIL, or distributive property. First, outside, inside, last. That gives me x minus 1 is equal to x squared minus 3x plus 9. I'm going to simplify the right-hand side a little bit. X minus 1 is equal to x squared minus 6x plus 9. Now at this point, thinking about what we had in lesson 3.6, we need to move everything to one side to get it equal to 0, and then factor, and then use our zero product rule. So I'm going to subtract x, and I'm going to add 1. I'm going to subtract x, and I'm going to add 1. This will equal 0. X squared minus 6x minus x is minus 7x. 9 plus 1 is 10. And then I'm going to factor this. So factoring this, I'm looking for two numbers that multiply together to give 10. Those same two numbers add together to give negative 7. Those numbers are negative 2 and negative 5. Because there's no value here other than 1, okay, there's an imaginary 1 there, I can factor by inspection. You can go through the whole process of factor by decomposition if you wish, but that's going to get me to x minus 5, x minus 2. And then here I use my zero product rule, just like in lesson 3.6, and I take each of those solutions, and I'm going to do it off to the side over here. Take each of those solutions, x minus 5, make that equal to 0, and the x minus 2, make that equal to 0. Simplify, I'm going to add 5. Add 5. X equals 5. I'm going to add 2. Add 2. X equals 2. So my two possible solutions, x equals 5 and x equals 2. So at this point now, we need to verify. So a first step in verifying, oh, we didn't do it. First step in verifying is that we should check our restrictions, which we didn't do So if we quickly figure out what our restrictions are, x minus 1, x, x having some technical difficulties with my pen here. So I'm going to take my x minus 1. That has to be bigger than or equal to 0. I'm going to add 1. X has to be greater than or equal to 1. There's our restrictions. Does our solutions, or do our solution values 5 and 2 fit this? Are they bigger than 1? Yes, they are. So there's our first step. Our second step is now we need to verify or test both of those values to make sure that it does work. So now we need to verify both those solutions, 2 and 5. I go back to my original equation, which was 3 plus square root of x minus 1 equals x. And I substitute in a 2, and then I do it again for the 5. 3 plus square root of 2 minus 1, that's a 2, equals 2. 3 plus 2 minus 1 is 1, 1 equals 2. 3 plus 1 equals 2. Obviously, you can see my pen is having some issues. So this is 4 equals 2. This does not work. It is not a solution. That's why we verify. So when we're doing these radical equations, and we have to do that squaring step, it causes some inherent problems in which we find solutions, we find numerical solutions, but those solutions may not fit the situation. So I've tested 2. Now I have to test or verify 5. I do the same thing. I go to my equation, 3 plus square root of, what was it, x minus 1 equals x. Put in a 5. 3 plus 5 minus 1 square rooted equals 5. 3 plus square root of 4 equals 5. 3 plus 2 equals 5. 5 equals 5. That is a solution. So although we numerically or algebraically find 2 values for this equation, 2 and 5, where is it? So here, 2 and 5, only one of them is a true solution. So that's why we have to do that verification step. It's really important. Okay. Let's move on before my pen completely fails on me over the page. So that situation here, where we get that solution of 2, but it doesn't work, this is called an extraneous root. Okay? Although we can find a root, we can find a solution. Okay? This is called, it's what we call an extraneous root. It's a root that actually we find but doesn't work. And that's what this description of an extraneous root does. And it talks about why we come up with them. Okay? And then again, just like I said, for this reason, it's always necessary to verify the solution to a radical equation solved algebraically. So now, like I said, we need to know how to figure all this out, put it all together. So here's our 2 examples. Let's start with A. Now, I'm going to run out of space. I'm going to have to erase part of it and then do question B. Okay. So here's A. Square root of A plus 10 minus 4. Our first step, somewhere as I want to do, there are restrictions. So somewhere off to the side, I'm going to go A plus 10 has to be greater than or equal to 0. I'm going to subtract 10, subtract 10. A has to be greater than or equal to negative 10. So there's our restriction. So we know that our solutions have to fit within that parameter. Now we go back here and we start to solve. Square root of a plus 10 minus 4 equals a. Our first step is that we need to add 4 because I need the radical by itself. Add 4 to both sides. These will cancel. This will give me square root of a plus 10 equals a plus 4. To get rid of that root sign, I need to square both sides. Square both sides. That's going to give me a plus 10 is equal to a plus 4 squared, just showing lots of intermediate steps. A plus 10 equals a plus 4 times a plus 4. That is a 4, by the way. I expand using FOIL or distributive property. I get a plus 10 is equal to a squared plus 4a plus 4a plus 16. I'm going to simplify my right-hand side a little bit. A squared plus 8a plus 16. Now I'm going to make everything equal to 0. So I'm going to move this a. I'm going to subtract a. I'm going to subtract 10. Subtract a. Subtract 10. My left-hand side will equal 0, because those will cancel. Equals a squared plus 7a squared plus 6. And then from 3.6, we're going to factor. We're going to look for two numbers that multiply together to give. Multiply together to give 6. Add together to give 7. Those numbers are 1 and 6. So this is going to factor a plus 1, a plus 6. Using my zero product rule, I'm going to take each of those. A plus 1 equals 0. A plus 6 equals 0. I'm going to subtract 1 here. That's going to give me a equals negative 1. I'm going to subtract 6 here. That's going to give me a equals negative 6. There are our two possible solutions, negative 1, negative 6. Now I need to go through the verification process. I'm going to check my restriction. Negative 1, negative 6. A has to be greater than or equal to negative 10. Both negative 1 and negative 6 are greater than or equal to 10. So that's my first step. My second step is I verify both. Okay? I go to my original equation, which is a plus 10 minus 4, which is square root of, I'm going to switch colors just so you can see it different. Square root of a plus 10 minus 4 equals a. I'm going to verify the negative 1. Square root of negative 1 plus 10 equals, oh no, sorry, minus 4 equals negative 1. Square root of 9 minus 4 equals negative 1. Square root of 9 is 3 minus 4 equals negative 1. Negative 1 equals negative 1. Perfect. There is a correct solution. So negative 1 is a solution to our system, or our equation. I do the same process for negative 6. Square root of, what was it, a plus 10? A plus 10 minus 4 equals a. I put in my negative 6, square root of negative 6 plus 10 minus 4 equals negative 6. Negative 6 plus 10 is 4, square root of 4 minus 4 equals negative 6. 2 minus 4 equals negative 6. Negative 2 equals negative 6. This is not correct, right? Not correct. So it is not a solution to our system, our equation. Okay. Because of my failing pen issue, and I can't possibly, well, maybe I can. You know what? I'll do this. I got to use my finger. So I've been using my finger the last little bit. It's a little bit harder to do. Okay? But this, I think this example will go a lot faster. So let's do example B. I'll do it on the other side of this. This way I don't have to erase. So negative 1 minus 2x. So somewhere I'm going to do my restriction. I'm going to say, well, let's go with negative 1 minus 2x has to be greater than or equal to 0. I'm going to add 1, negative 2x has to be greater than equal to 1. Divide by negative 2, divide by negative 2. Those will cancel. X, flip my inequality, has to be less than equal to 1 over negative 2. So negative 1/2. There's our restriction. Now I can go through the process of solving. So my first step, because if the radical is isolated, that's perfect. I'm going to go this squared, this squared. I'm going to jump way up over here. So now I have negative 1 minus 2x is equal to x squared. I need everything equal to 0, and you have two options. You could actually move the x squared this way because it's one step, but then you're going to be dealing with negative x squared minus 2x minus 1 with this negative sign out in front, and it gets pretty ugly when you're trying to factor. So you want to always try and keep your x squared value positive. So I'm going to add 1 and add 2x here. I'm going to add 1 and add 2x here. Now you can see everything's positive, so it's going to make our factoring much simpler. 0 is equal to x squared plus 2x plus 1. And then I factor. I look for two numbers that multiply together to give 1. Those same two numbers add together to give 2. 1 and 1 equals x plus 1. X plus 1, 0. I use my zero product rule law from 3.6. X plus 1 equals 0. I don't have to do the other one because it's exactly the same, so I'm going to have to do this once. I'm going to subtract 1. X equals negative 1. There's my possible solution, and now I verify it. Does it fit within my restriction parameters? Has to be less than equal to negative 1/2. Negative 1 is less than or equal to negative 1/2. So now I test it. I put it into my original equation. Square root of, I'll test in a different color, or verify, sorry, I keep saying test. Square root of negative 1 minus 2x equals x. Is that correct? Yep. So I'm going to put in negative 1, square root of negative 1 minus 2 times negative 1 equals negative 1. Square root of negative 1. Negative 2 times negative 1 is plus 2 equals negative 1. Square root of 1 equals negative 1. 1 equals negative 1. This is not a solution. So in this case, because we're only verifying one value, this equation, we actually say no solution. No solution. Okay. Well, I was glad I got through that. The questions are posted or noted somewhere. You know what to be working on. We will see you next time.